Good afternoon. It is so good to see you all here. Today, we are here to talk about something that has been a game changer for us here at Zomato, which is the Kuma Service Mesh. We are using it not just to scale with reliability, but also to improve the developer productivity. But before diving into the details of it, I would like to introduce ourselves. So I am Arpit Mishra. I've been a part of Zomato since past 2.5 years, and I've worked on the service mesh and the incident management. Later, I worked on the developer productivity tools. Prior to this, I worked at Glance, and I recently started contributing to Kuma. Deepak, would you like to introduce yourself?
So, hello everyone, I'm Deepak Verma. I'm staff site reliability engineer at Zomato, and I did the setup of Kuma and migrated our existing service mesh to it. Yes, and recently I started managing Nugget, which is our chat-based SaaS platform.
Thank you, Deepak. Yeah, to give you the sense of the scale we are operating at, Zomato is not just a food delivery business. Under the hood, it is a complex ecosystem of microservices interacting with each other under very heavy load. So we have over 500 microservices, each with their specific purposes, from order placement to logistics to merchants, payments, and many more. On a normal Sunday peak, our services are scaled up to 13,000 plus data planes, and our peak throughput reaches around 200 million RPM across services. So any performance degradation in the network can cause a serious downtime for us. Sorry, yeah. So this is the agenda of this talk. So first, I'll start with the beginning, why we felt the need for a service mesh, what challenges we were facing, and what pushed us down to explore Kuma. Next, we will talk about the overview of Kuma, how it is different from the other service meshes. Next, we will talk about how we are actually leveraging Kuma. And finally, we will talk about the developer productivity tools that we have created. So the beginning. Back in 2008, Zomato was just starting out. And as any other startup business, we also started with a single monolithic application. And all the features from restaurant listing to searches to reviews, all were written onto the same code base. In 2015, Zomato launched its online ordering business. So the new workflows, new integrations, new user experiences, all were piled up onto that same monolithic application. By 2016, we realized that our monolith was making us slow as the developers' team size has increased and our feature velocity have grown too. So we needed a better way to manage that. So we migrated to the microservice architecture. We started following it. So over the time, we broke into multiple microservices, and all were deployed on the AWS ECS. Around 2019, Zomato had almost 30 microservices, and so then we started facing the other challenges, as in the service connectivity, the observability. So we needed a better way to manage that. So at that time, we decided we should move towards the service mesh architecture. Deepak, now can you go?
Zomato began its service mesh journey on AWS ECS. So AWS ECS is service orchestration service just like Kubernetes. Router used static configuration for service routing and relied on ECS API calls for service discovery. This slide basically highlights some of the key challenges we faced with Router. All communication between services was using plain text. So there was no traffic encryption in transit, which was a security concern for us. When a service started, it needed to discover all other services in the mesh. This caused noticeable delays during startup, especially as our service mesh grew. Although Envoy was at the core, our setup did fully utilize all its features. Basic features like traffic splitting, mirroring were not usable at all. Finally, each new service or configuration update required manual updates. We had to maintain Envoy's bootstrap configuration separately for each service, so there was no standardization. Updates were risky and difficult. because we didn't have clear visibility into different Envoy versions across all the services. A single static configuration could easily have compatibility issues with different versions of Envoy. Since all services depended on the same static configuration, a single mistake could easily cause failures in our entire service mesh. These pain points were the major driver for evolving our service mesh. Once we identified the limitations of our early service mesh, we evaluated several alternatives. Firstly, both Istio and traffic were powerful, but are Kubernetes native. But since our workload is on AWS CCS, adopting Istio was not a viable option for us. Linkerd is lightweight and fast, but adopting it is not possible for us because it was using Envoy. Since we had spent expertise on Envoy, migration to Linkerd meant a steeper migration for us. AWS App Mesh integrates seamlessly with other AWS services, and it supports AWS CCS as well. But its configuration options were quite limited at that time, so we decided not to go with it. After evaluating the alternatives, we decided to adopt Kuma as our service mesh. Kuma is platform agnostic and supports workloads across orchestrator like AWS ECS, Kubernetes, and VMs like EC2, and even multi-cloud environments. Kuma supports multi-zone architecture natively and integrates and has seamless Envoy integration. Kuma ensures a cleaner separation between control plane and data plane, making the architecture simpler. Now that we have chosen Kuma, let's take a deeper look how it works and what makes it a good fit for us. So as mentioned earlier, Kuma is a Envoy-based service mesh. It is developed by Kong and has been a CNCF project since 2020. It supports both L4 and L7 traffic instrumentation, meaning we can control both the TCP level traffic and HTTP level health checks and policies and routing within the same mesh. So this is basically how single zone deployment model of Kuma look like. It basically consists of two components, Kuma data plane and Kuma control plane. So Kuma data plane, referred to as Kuma DP in the image in the below, connects to the Kuma control plane and is responsible for the service-to-service communication. Kuma data plane is built up of Envoy sidecar proxies, which runs as a sidecar alongside each service. Kuma control plane, referred to as Kuma control plane, Kuma CP in the image, is basically the brain of the mesh. It maintains the state and policy of the mesh. It accepts the connection from the Kuma data plane and maintains an inventory of all the data planes running inside the mesh. Based on this inventory, it configures the Kuma data plane for the communication. It keeps the inventory in the Postgres or memory or the Kubernetes store. And this is how Kuma ensures a cleaner architecture. Now let's talk about the multi-zone. Support in Kuma. So first of all, what is a zone? So a zone can be anything, an ECS or Kubernetes or a VPC or any environment we want to bring in a mesh. What is a mesh? A mesh is basically an isolated service boundary for policy and services. Services can span across multiple zones, but a service in one mesh cannot talk to service in another mesh. On the right, we have several zones, zone X, Y, Z, each consisting of a data plane and control planes. Each control plane can also be labeled as a remote control plane or zonal control plane. So, each data plane connects with their local remote control plane only, and remote control plane receives connections from the global control plane and is responsible for configuring those data planes. It performs a similar role as in the single zone deployment model. Global control plane accepts the connection from each zone control plane and configures them. Another job of global Kuma control plane is to provide the UI for all the components in the mesh. Global Kuma control plane also maintains an inventory of the mesh-wide policies and all the data planes running inside the all the data planes running across all the zones. One thing we haven't touched in this slide is the cross-zone communication. So the cross-zone communication is enabled through the use of zone ingress and egress proxies. So when a service needs to talk to another service in another zone, the traffic goes via the zone ingress and egress proxies. These proxies are just like other data plane proxies, but these are meant for interzonal traffic only. Global Kuma CP synchronizes the policies and configuration for these proxies and sends it to the remote Kuma CP. Remote Kuma CP then configures those zone ingress and egress proxies. Kuma's architecture is, let's understand how Kuma handles scaling. Kuma's architecture is able to handle scale naturally. Control plane is horizontally scalable, and while the data planes, since they are deployed as sidecars, scale linearly with our microservices. We don't need to scale them separately. Kuma uses incremental configuration updates. So rather than sending the entire configuration each time during updates, is only sending the delta of the configuration, thereby reducing the load on the control plane and also reducing the network usage. So in our mesh, one control plane is able to serve around 700 to 1,000 data planes while keeping the configuration delivery latency low. So far, we have talked about how Kuma works. Now let's talk about how Zomato uses Kuma to boost its production reliability and developer productivity. Kuma supports policies like traffic permission, traffic route. These policies are just like the resources in the Kubernetes manifest, but these policies are used to generate data plane configuration. Our usage is built around these policies. So we have the standard policies pre-applied. And developers can override these policies through GitOps. This GitOps-based approach ensures central governance for our SRE team, and also it ensures the drift prevention across our environments, making prod and staging consistent. Kuma also implements zero trust model policy for us, using its traffic permission policies. Using its traffic permission policies, it also ensures mutual TLS between the service-to-service communication. Kuma also takes care of the certificate handling for us. So it has a built-in certificate authority which manages a certificate for us, and it is responsible for the creation and rotation of these certificates. So this completely avoids the manual handling of these certificates, thereby avoiding any risk of making errors. Kuma supports gRPC, HTTP, TCP health checks. We use a combination of active and passive health checks. So what are active health checks? In active health checks, Envoy proxies proactively sends a probe to the upstream members to determine whether they are healthy or not. While in passive health checking, it is done via outlier detection, where it is determined dynamically whether the hosts are performing unlike the others or not. So in the diagram on the right, we have a service A communicating with service B. So since pod A is responding to the health check probes, it is healthy and will be included in the healthy set. While the pod C is not responding to the health check, so it will be excluded from the load balancing set. Pod B, since it is misbehaving, it is temporarily excluded from the load balancing set and will be added back sooner or later. This is the way Kuma ensures that healthy data planes handle production traffic. Kuma also gives us the mesh-wide observability. So we collect the we collect the request to connection level metrics from the Envoy sidecar proxies and ingest them into our Victoria metrics or Prometheus, and then visualize them on Grafana. So this way, we don't need to add any instrumentation in our services and get a complete view of our mesh. So Kuma also helped us to unlock Canary environment. We use Canary environment to ensure that any new version of service is rolled out only to a subset of users first. So for our Canary environments, we rely on Kuma's traffic route policy. So on the right, we have a policy named Canary deployed in our production mesh targeted for our microservice promo service. So in this policy, basically 5% of the traffic will go to the promo service Canary, while 95% of the traffic still goes to the stable promo service. So now we were using Kuma for other features also, like load shedding and fault injection for our chaos environment. But now Arpit will cover how Kuma unlocked new pathways for us to accelerate developer productivity.
Thank you, Deepak. So as Deepak said, I'll be talking about how we accelerated developer productivity using Kuma. So, but in order to understand it fully, we will first have to understand how Zomato's development workflow looks like. So it is mostly similar to any other organization. We first develop our code locally and test it there. Then we push it to a remote repository, which in our case is GitHub. We raise the PR, then the code review and merges. It gets deployed to staging. Once tested on staging, it gets deployed to pre-prod and tested, then to Canary, and finally to production. But there were few challenges in this flow. As in, the pull request takes a lot of time to get reviewed, and it is difficult to test microservices locally in a large ecosystem like Zomato, because we have over 500 microservices, and all of the microservices are depending upon some other microservices. So in order to test them end-to-end fully, you will have to run all their dependencies in your local machine, which is not very possible due to the resource constraint of the local machine. And also, even if you push your changes to the staging environment, then also it cannot be considered as safe, because this is the first time we are running it end-to-end. So like a one bad change can be can result in a broken flow for everyone. So if I push a bad code in the staging, so all the services that are depending upon my service will also get impacted during testing. So we needed a better way to manage this. So we introduced a new workflow, that is the preview environment. Yeah. So it was an ephemeral environment, parallel to staging, and deployed for every pull request. It lets you shift left in the development cycle, so faster feedback loops. And also, your bad changes will not impact any other environment, as these are going to be your ephemeral environment, and it will be for you only. So how this actually works? So just consider this is a normal staging environment. There are downstream services. There is one promo service, for which we are giving example of. There are upstream services. So downstream service will call the promo service, and the promo service must be having some upstream service dependencies, so it will call that. Preview environment just comes in parallel to the staging environment. So we just deploy a preview environment of promo service. And as soon as we are going to route our call using a HTTP header preview ID, the calls are going to route it to the promo service, which is of the preview environment, not the staging one. So that is how we ensure that the normal code flow will work exactly as is. Only our changes will get impacted, and only our call flow will be able to test this new code. So how is this routing actually working? So let's unravel this routing. So this is powered by the Kuma's traffic route policy. We are relying on the preview ID header. So we can just take an example of this sample traffic route policy. So if call is coming from anywhere, that is why we are using the wildcard entry in source to the promo service. By default, the calls are going to go to the promo service with label default. And if the preview ID is matching the regex promo service -1234, where 1234 is the pull request number, this is how we are using it in Zomato. The calls are going to go to the promo service of preview environment with label promo service -1234. So this is how actually it is working. There's one requirement to it that we will have to ensure that the header is propagated in all of our microservices. So let's say in our call flow, 3 or 4 microservices are included. So we have to make sure that each one of them is actually propagating the header. So because like if any one of them is going to drop the header, we won't be able to route it to the preview environment as we are completely relying on that header. Now even the preview environment was taking some time. As in, you have to, commit your code, then raise the pull request, then the service build time, and the service orchestration time. Then the health checking is there, service startup time is there. So as we say in Zomato, it's still 1% done. So we just thought, how good is it gonna be if we can test everything locally? Which led us to implement our game changer, local preview. Now you do not even need to push your code to the remote repository. Just run your code locally and the request will come to it. We are using local proxy service as a bridge between the staging and the local environment. And its routing is also powered by Kuma's traffic route policy as we are doing in the preview environment. So how is this magic working? So just look at this diagram, and on our cloud, staging environment is there with some downstream services, then the local proxy service is there, and a developer is there. Developer is outside the cloud, obviously. So developer will first call the local proxy service and reserves a port for itself. Then it makes a SSH reverse tunnel to the local proxy service on that particular port. Now, whenever the staging environment's downstream service is trying to call the local service using the preview ID header, as I mentioned in the preview environment, the calls are going to come to the local proxy service, again using the Kuma's traffic route policy. After that, this local proxy service already has the mapping of the preview ID to the port because the developer actually first registers the port. So it has the mapping. So it just asks for it. And then the envoy forwards all its traffic, all the incoming traffic to that particular port. This is how the call is coming to a local developer's environment. So yeah, that's not it. We still have more cooler things to do on our plate. These are the few things that we wanted to cover here. So the one is the availability zone aware load balancing, in which we are trying to use the invoice zone aware routing this is a cost optimization track. And then the other one is the gRPC compression. This is again a cost optimization track. Next, we are planning to migrate to the open telemetry because this will improve our observability stack. And also, we are trying to implement automated traffic failover from Canary to prod based on the error rate, as Deepak explained the Canary environment. So whenever a new code gets pushed to the Canary environment, and if there's any error to it, we automatically want the failover to go to the production environment in order to protect the production traffic. That is all from our side. If you guys have any questions, so feel free to ask. Yes. I'm sorry. Can you use the mic?
Can you please tell that SSH reverse tunnel thing in a little bit elaborated manner?
Okay.
And why would you want to use that? Instead, you can use something like mirror D, right? That can mirror your requests that are going to staging onto your dev.
Okay, I'm not aware of about this. What did you say? Mirror D?
Yeah.
Okay, I was not aware about it. I can look at it, and you can just contact me on LinkedIn. We can discuss it over there.
No worries.
Sure.
But you can tell about SSH reverse tunnel in a bit elaborated manner, please.
Got it. Yeah. So basically, this SSH reverse tunnel, it just reserves a port because we have to, we can only, reserve a single port for a single developer. So that is why we call, and the local proxy service checks for the available ports, and from that pool of port, it just provides the developer one and remove it from that pool. So this is how it is actually making the SSH reverse tunnel. And we are using actually we do have a internal command line tool called zctl, which is not actually a part of this. From that, we are using all these things. That zctl command actually calls the local proxy service, gets the port, then makes the reverse tunnel. So to a developer, it does not mean like it is not like he or she has to know everything that is happening behind the scene. Okay.
I have a question.
Yeah.
So what I understood, the main reason for going to Kuma, because we have a hybrid environment, not
Yes.
only Kubernetes. Is it still there? Like you have VM also and the Kubernetes? That is the only reason you are with Kuma service only?
We are actually deployed on the AWS ECS, as we said before. So we do not have Kubernetes yet.
Okay.
We are deployed on AWS ECS, so that is why we needed Kuma.
So not sure if you can, so let's say example, if my environment Kubernetes only, and we have few popular service mesh, Istio
Yes.
or Cilium,
Yes.
and let's say example Kuma.
Yes.
So example, can you give me or help us with some scenario where maybe Kuma can be right fit in over the other mesh?
It is mostly related to that if, like, as in you don't know that where your environment is gonna be in next 5 years, 5 or 6 years. So let's say you are currently deployed on Kubernetes, but in future you wanna move to a VM or some other service orchestration tool comes in, and you wanna move to there. So Kuma provides a universal playground. Like you can implement it anywhere. So that is the main advantage of Kuma, which we have saw.
Okay,
Yeah.
thank you.
So I had a here.
I'm sorry. Yes.
Yeah. So I had a question. Two things. First one being for the. So you mentioned that you are on ECS.
Yes.
Right. So I think now Istio. So my question is from an Istio perspective is now that Solo IO has a integration with for ECS as well, where the data plane happens in the ECS and the control plane is being managed somewhere in an EC2 or Kubernetes. Like you can pick and choose your deployment environment for
Control planes.
your control plane,
Yes.
but data plane is in place. So one thing that Istio has there, and so I was just curious on the choice of Kuma. And so from what I understand, Kuma is also like a sidecar-based thing,
Yes.
right? Does it also offer something like Z-tunneling or the ambient thing that Istio has come up with? Because I think latency numbers are very low when you look at ambient. So my follow-up question is, have you all, done like performance on it, like the Kuma? And is it does it add significant latencies and significant resource consumption compared to Istio in ambient mode? So, so basically, your choice between Kuma and Istio, that is something that I wanted to understand more about, and two numbers.
Got it. Deepak,
Yeah,
would you like
so,
to answer?
When we migrated to Kuma, at that time I think Istio in ambient mode was not available, right? But right now we haven't evaluated the performance between Istio in ambient mode and Kuma. But yeah, since Kuma is also just an envoy proxy running sidecar, so I think the latency will be almost similar for both the scenarios.
But ambient is not, ambient is sidecar less.
Yeah, that is EBF based, EBPF based, right?
Yeah, EBPF
Yeah.
based, right.
So I have to check on that, what will be the latency difference between them.
Got you.
What was your experience with running stateful applications here? Here.
Sorry.
So
Okay.
What was your experience with running stateful applications like stateful sets, which involve in leader election basically with MTLS on with Kuma service meshes? Because I have seen on other service meshes, they particularly have problems with stateful applications which do leader election on custom TCP protocols. Like Kafka is one of the case. Have you run into such use cases with Kuma service mesh?
No, so we haven't, we are not running any such use cases on Kuma, but I think we will be able to consider each data plane as a separate service, so that the service mesh host name will be mapped to the corresponding host. Then I think we will be able to run such applications.
Hello. Hi.
Yeah.
I had a question for you guys. So if the local service that the developer is running on their system, let's say if it's a backend service and it needs to connect to like a data store or a queue or something like that, how does that connection work?
We already have that in place. We have not covered it in this slide because it would have been out of scope for that. We are using internal VPN tool for this that our local developer can connect to any upstream service present in the staging environment and also the data stores as well. It can connect to any.
And how do you manage the state of, let's say, if the person is testing a certain branch and it needs to connect to a certain new infra, where is that metadata handled?
This is a kind of like the experience-based approach that we tried it out, and surprisingly it worked. We also had the similar concern in our mind, but till now we had not had any problem with this approach. So yes, we are working it, but we do not have any like clear answer for it.
But the connection, does that happen through the reverse SSH tunnel or directly
No.
to the infrastructure?
That is through a
From
VPN.
your VPN.
Yeah.
Okay. Thanks.
I have a question here. Here. How do you guys manage deploying the data plane in case of ECS or EC2? Because my experience is with Istio in Kubernetes, where it's automatically done, sidecar injection is automatically done. But how do you guys manage the data planes deployment as well as upgrades?
So that is manual, still manual, because ECS does not have anything like admission webhooks in Kubernetes. So that is done manually currently via some scripts or internal tooling we have.
But adding on top of what Deepak said, we also have automations for it that when you orchestrate the service for the first time, it just adds the Kuma DP as a sidecar in it, and then we update only the main containers, like as in the services main container image only. So basically, Kuma DP will not be impacted by that change. So that is how we are actually managing it.
One thing I want to add is that Kuma also supports automatic sidecar injection on Kubernetes, but on ECS it doesn't.
There may be a follow-up question, right? In Kubernetes, both the containers are considered as a pod, and if even one of the containers becomes unhealthy, the pod itself is considered as unhealthy.
Yeah.
In your case, I believe these two are two different components. How do you manage?
No. So on ECS also, both are considered similarly like a pod. So if the Kuma data plane is unhealthy, the task will be unhealthy and it will be stopped by ECS.
Okay, and you have any deployments in EC2 then? No.
Currently, I think one service is running in EC2, but others are migrated on ECS.
Okay.
Hi.
Yeah.
So I have two questions. So you talked about header propagation. Was it achieved by code changes, or was it some library used to propagate the header to the downstream services?
It was a library actually. We use common libraries for the operations like gRPC and Kafka, all these things. So in the gRPC library, it is there.
Okay.
And also in the Kafka library as
Okay.
well. Yeah.
And second question, you talked about all the version propagation for HTTP-based communication.
Sorry, version propagation, you said.
Yes, basically the preview environment.
Got
But
it?
if services are event-driven, let's say they are talking
Yeah,
via
yeah, yeah.
consumer subscriber model or SNS SQS, have you solved that problem, or did it come to your attention that how the context information is propagated in event-driven architecture?
Okay, so in the event-driven architecture, we have a solution for the Kafka because Kafka supports the Kafka metadata. So that we already do. For the SQS, I don't think we have a solution
so
yet, right?
SQS was a bit hard to do, so we haven't done that yet. But we have an inbuilt solution, worker controller. So what it does, it consumes the message from the SQS and makes HTTP request to the downstream services. So all the consumers will be basically like HTTP services, right? And this worker controller will be responsible for the header propagation. So that's why we didn't do that SQS, do that for SQS. But because we are in the process of migrating our workloads to worker controller.
Thank you.
Okay. Cool. For the rest of the guys, if you guys have any question, feel free to ask offline.